Hi guys, welcome back. In this video we're going to evaluate this improper integral and one more if we have time, depending on how long this particular one goes. I think this is pretty much a classic example. Lots of math teachers love this improper integral. It's the integral from negative infinity to infinity of this function right here. If you graph it, actually you can see if I plug in x equals 0 here, I'm going to have e to the 0 is 1, and e to the 0 is 1. So I've got 1 over 1 plus 1, so this is going to be 1/2. And then it just looks like this. And what we're looking for is the area under the curve from negative infinity to infinity. But notice we've got two problems. We've got the problem on the left and the problem on the right. That's making them improper. So we're going to split this up into two integrals. One is the integral from negative infinity to anything we want. I'm just going to choose 0, because 0 is nice and simple to plug into functions. And then the second one is the integral from 0 to infinity of the same thing over here. Alright, if this one converges, and this one converges, then this one converges, and it converges to this plus this. If one of these diverges, that one diverges. So this first one, this first guy right here, this is going to give us a sense of the area on the left. So we're looking at the area from negative infinity to 0. We want to know if that's finite or not. And then this one will give us a sense of the area on the right. We want to know if that's finite or not. So we're only going to work on one of these at a time, and then maybe there won't be so much work to do. Maybe one of them will diverge and we can be done. We'll see. Let's do this purple one first. I'm going to call this integral double star. And do that. So we're going to take the integral from 0 to infinity of e to the x over 1 plus e to the 2x dx. First we notice that it's improper, so we write it as a limit. The problem occurs at infinity. The problem occurs at that upper bound. That means we've got an infinite domain, an unbounded domain, so we have to write it as a limit as b goes to infinity of the integral from 0 to b of e to the x over 1 plus e to the 2x dx. And again, remember what that means. I'm going from 0 to b, and I'm going to find that area. And then the question becomes, what happens to that area as b goes to infinity when I'm done? So we took care of the first step. The first step with every improper integral is to write the improper integral as a limit. And it's always the limit of a proper integral. This one's proper. I can apply the fundamental theorem of calculus to this. So now I'm going to ignore the limit for a while. I'm going to keep it going on this side because in order for everything to be equal, I need to keep having that limit there. But I'm ignoring it almost. I'm just bringing it along for the ride while I focus on this part. So now I need to apply the fundamental theorem of calculus. So the first thing I need to do is anti-differentiate this function. And it's not 100% obvious what to do. We've got an e to the 2x here. So if I let u be the denominator, the derivative of e to the 2x, or derivative of 1 plus e to the 2x is 2 e to the 2x. And I don't have an e to the 2x up here. I only have an e to the x. But if I use a little bit of algebra, I can rewrite this, and we'll be able to do a u-substitution. Now remember from algebra that if you have an x raised to a power and you raise the whole thing to a power, you multiply those exponents. There's a very good reason for that. We won't go into that in Calc 2, but there's a very good reason for that. Now that's going to work no matter what the base is. If that's an e instead of an x, it still works. And it actually goes both ways. So typically I would take something like this in my algebra class and I'd simplify it to write it like this. But also, if I've got a product over here, I could rewrite it as a power raised to a power. Like that's what this says. This is the same as this, and this is the same as this. So e to the 2x, I can think about that differently. I can think of that as e to the x squared, because 2 times the x gives me that 2x that's right there. And now I see a u sub. You see a function nested inside another function? I hope you do. So those parentheses, that's my u. And I know this will work because when I take the derivative of u, what do we get? Get e to the x dx. This has to be up there as a factor somewhere, and it is. There's an e to the x dx right there, so I can write everything in terms of u. So I'm going to write the integral in terms of u. I also need to plug in x equals b and x equals 0 to get new bounds. When x equals b, u equals e to the b. When x equals 0, u equals e to the 0, which is 1. So this is the limit as b goes to infinity of this new integral. Every single part here needs to be accounted for. The e to the x dx, that's my du. The upper limit, x equals b, gets replaced with the new upper limit, x equals, or u equals e to the b. And then the lower limit, x equals 0, is replaced with the new lower limit, u equals e to the 0, which is 1. Now there's no e to the x there anymore. That was taken care of by the du. So there's an implied 1 in the numerator. And down here, we've got a 1 plus, and that's a u squared. I hope you remember this rule. Remember? That's an arctangent. Our rule for arctangent has an a squared plus x squared. Here a squared is 1, and instead of an x squared, we've got a u squared. A squared is 1, so that means, of course, a equals 1. And the antiderivative is the arctangent of my variable over a times 1 over a. A is 1. And my variable is u instead of an x. I know that dividing by 1 is kind of overkill. We'll simplify that in a minute. But I just wanted to show you where all those pieces came from. Okay, now I've computed the antiderivative, and now we use the fundamental theorem of calculus, so plug in the upper limit, plug in the lower limit, and subtract. All right, here we are. Now we can simplify this. It can be simplified quite a bit. A couple of things that we need to know, though. We need to know what the arctangent graph looks like, because as b goes to infinity, e to the b also goes to infinity. So I need to think about what happens to arctangent as what's inside goes to infinity. I need to think about that. And then I might also have to remember a little trig to remember what arctangent of 1 actually means. Arctangent of 1 is an angle. And it is the angle whose tangent is 1. That's what an arctangent is. And there are some restrictions on the values of theta that this can take on. Theta has to be between negative pi over 2 and pi over 2. I know it's been a little while since trig, but it's got that angle has to be in quadrant 4 or quadrant 1. And it turns out tangent is 1. We know, and theta is 45 degrees, or we're in calculus, so pi over 4 radians. So this is pi over 4. Now for this part, I need to know what arctangent looks like. For that, it's helpful to recall the tangent graph. You remember tangent? It's undefined whenever cosine is 0, because it's sine over cosine. You can't divide by 0. So it looks like this. It repeats forever. Now, this is the tangent function. It does not have an inverse, not as it stands. It fails the horizontal line test. That horizontal line crosses 4 times. But if I just focus on this one piece, it does have an inverse. If I restrict myself to this one piece and I switch x and y, then I see something that looks like this. That's the arctangent graph. And this is very helpful. Very helpful because as x goes to infinity, as what's inside gets very, very large, the y values approach this this horizontal line. And this horizontal line came from switching x and y, and it came from this vertical line. When I switched x and y, x equals pi over 2 became y equals pi over 2, and x equals negative pi over 2 became y equals negative pi over 2. So as e to the b goes to infinity, arctangent of something very large is approaching pi over 2. So this is approaching pi over 2, and that is approaching pi over 4. So I've got half of pi minus a fourth of pi. That's a fourth of pi, and that's great. This part converges. It converges to pi over 4. All right, so this part on this side, as b goes to infinity, this side approaches pi over 4. And you might be tempted to say, oh, symmetry. I don't think that we get to do that because of the e to the x in the numerator. Yeah, I don't think there's exact symmetry here. Going from negative infinity to 0 is not the same as going 0 to infinity for e to the x. So that's disappointing. But this one converges, so maybe this one converges, maybe the whole thing converges. To figure out if the whole thing converges, I need to look at this integral. So let's evaluate this one, and we'll see what happens. Before we do that, though, let's just review real quick 3 steps to evaluating an improper integral. First, you write it as a limit. This is one of the most important steps. It tells me that you know what an improper integral is. Improper integrals are limits, and they're limits of proper integrals. And then the next thing we do is apply the fundamental theorem of calculus, which requires anti-differentiating, and of course, you do f of b minus f of a after you've computed the antiderivative. So that's the second step. You could get hung up here if you don't know how to write that improper integral as a limit, or you could get hung up here if you know you're supposed to anti-differentiate but you can't. So make sure that you know your u-subs, make sure that you know integration by parts, make sure you know all of the basic rules that we've talked about so that you can take this antiderivative and then apply the fundamental theorem. And then the last part, where it's very easy to get hung up because it's been a while since Calc 1, is to go from here to here. You have to evaluate a limit. And that might require L'Hopital's rule, as we're going to see in another example, or it might require some knowledge of a function you haven't used in a while, like arctangent. So make sure that you're prepared to evaluate limits of continuous functions. This is Calc 1 stuff from the very beginning of Calc 1. You can't forget it. Unfortunately, it comes back again. And it's related to this beautiful area problem, this finding the area of this unbounded region if it's finite, if it exists. Okay, so we've got to be able to write the integral as a limit, apply the fundamental theorem, and then evaluate the limit when we're done. So let's finish this problem. I think I'm just going to do one problem in this video because I'll just say this is another example. This one is getting pretty long. We're going to do that one now. So I've got the integral from negative infinity to 0 of e to the x over 1 plus e to the 2x. And this is actually not that bad because we did the hard part. We already know the antiderivative. First, we're going to write it as a limit. The problem occurs at negative infinity, the lower limit. So I'm going to replace that with a. I'm going to do the same thing I did before. Now this is a limit of a proper integral. So I can apply the fundamental theorem of calculus to this. All right, and we already did the work. U is e to the x, du is e to the x dx. So that's u, that's du, and we have a 1 over 1 plus u squared du. Now we need some new bounds. When you substitute an x equals 0 here, e to the 0 is 1. When you substitute a here, you've got e to the a, or excuse me, u of a is e to the a, excuse me. So that's my new upper limit, that's my new lower limit. Just bringing my limit along for the ride. All right, now I've got 1 over 1 plus u squared du, and my new upper limit is 1, my new lower limit is e to the a. Okay. So we applied the fundamental, or we started to apply the fundamental theorem by doing a u-sub. And now we need to anti-differentiate and then compute f of b minus f of a. And then we're done with the fundamental theorem part. We know from before the antiderivative of this is arctangent of u. We're going to evaluate from u equals e to the a to u equals 1. So we've got arctan of 1 minus arctan of e to the a. Careful here, guys, that is not pi over 2. A lot of students want to say it's pi over 2. You got to think this through. I know it looks a lot like the last one, but it's not exactly the same. Okay, now I need to think about what happens. Arctan of 1, that hasn't changed. That's still pi over 4. Tangent of 45 degrees, or pi over 4 radians, is 1. So we're good there. But now I have to think about what happens to e to the a as a goes to negative infinity. Now this is what the function y equals e to the x looks like. As x goes to negative infinity, the y's on the graph get very close to the x-axis. So this is approaching 0. It's not approaching infinity this time. I've got e to a large negative power, like plug in negative 1,000. E to the negative 1,000. Remember with our exponent properties, that's 1 over e to the 1,000. That's 1 over a very large number. 1 over a large number is a very small number. So this is very small. Arctangent of something very small, something close to 0. It's 0, guys. That's arctangent. Arctangent of 0 is 0. Now I know my graph isn't great. But yeah, that's the basic idea. This is y equals arctan of x. And it looks like that. This is approaching 0. Arctangent of 0 is 0. And so it turns out we get pi over 4. So we had a picture that looked like this. I'm not doing a very good job with my graphs tonight. We already took care of this, and we found out that that area in some limiting sense was pi over 4. And we wanted to know what was happening over here. So we took the integral from negative infinity to 0. We wrote it as this limit, the limit from a to 0. We found this right here. And then we said, what happens to this as a goes to negative infinity? As a goes to negative infinity, turns out we're subtracting something. We're subtracting this piece. And it's getting very close to 0. So close we're going to call it 0 in the limit. And then this area here, when we take all of it, is pi over 4. So the original integral, the integral that we started with, is the pi over 4 plus the pi over 4. So that's pi over 2. It's half a pi right there. Pretty cool, huh?